This is a look at the physical origin of most legacy audio collections. Decades of ripped CDs, downloaded files, and archived web audio, all piled onto a single hard drive. This diagram shows the messy reality of that data. When you play these files back to back, you hit severe volume disparities, followed by long, flat trails of dead air at the end of tracks. The target hardware for this audio is a screenless bone conduction headset designed to be used completely submerged in water. This device has zero network connection, no API, and no capacity to read metadata. Its entire operating system relies on basic alphabetical file name sorting. Loading a folder of disparate files and hitting shuffle creates an abrasive experience. The volume spikes, the dead air drags on, and the lack of context makes a random playlist feel entirely disconnected. Solving this requires doing the computational heavy lifting before the audio ever reaches the player. We have to pre-compile the sequencing intelligence and the auditory context directly into the files themselves. The objective is to turn a static folder of MP3s into an offline radio station, complete with a context-aware DJ speaking between the tracks. The standard engineering approach would be to write a massive Python application to handle audio processing, file parsing, and AI generation all at once. That creates a brittle, monolithic system. The alternative is to apply the Unix philosophy. Build small, highly specialized command line tools that do one thing perfectly, and chain them together using a plain text specification. This schematic outlines the 4 distinct computational nodes we will use: amplitude normalization, boundary trimming, persona emulation, and AI orchestration. By favoring composition over monolithic code, we bypass severe hardware limitations through flexible, isolated software constraints. The first node in the pipeline tackles the chaotic volume disparities across the legacy files. This is a professional audio mixing console illustrating the core concept of broadcast mastering. True volume standardization requires analyzing the integrated loudness of the entire track over time, rather than simply clipping the highest audio peaks. To achieve this, the MP3 norm tool applies the EBU R128 broadcast standard to bulk normalize the entire directory. This chart details the 2-pass loud norm technique. Pass 1 measures the jagged source waveform. Pass 2 applies a single linear gain adjustment, scaling the entire audio block cleanly to align with a persistent -14 LUFS target, without applying destructive dynamic compression. Once processed, the tool stamps a custom tag directly into the file's metadata. This acts as an idempotency mechanism, allowing subsequent runs of the tool to safely skip files that are already normalized. This converts a wildly unpredictable dataset into a mathematically uniform foundation. The listener never has to reach for a volume knob. The second node addresses the ends of the files, eliminating trailing dead air, sustained applause, or radio host chatter. Basic threshold-based silence detection fails here. If a live track ends with 30 seconds of audience cheering, the volume never drops to 0, so a standard gate won't trigger. Instead, we use MP3 trim, powered by a convolutional neural network called ENA Speech Segmenter. The CNN explicitly sorts the audio spectrogram into music, speech, and noise. At the far right edge, we see the boundary logic. The tool locates the last music segment, adds a half-second guard buffer, and executes the snip. This cutting operation doesn't re-encode the file. It uses a lossless stream copy that snaps precisely to the nearest MP3 frame boundary, preserving the original audio quality. Combining neural network classification with functional boundary logic cleanly isolates the music from the trailing junk, leaving the source data perfectly intact. The third pipeline requirement is generating the DJ's voice to contextualize these cleaned audio tracks. We avoid generic AI assistant tones. A radio station requires personality, so we emulate the specific writing styles of famous comedians. This relies on the claude-standup-skills repository, which codifies the rhetorical patterns of different performers. These skill files act as structural constraints. They force the large language model to operate within a specific comedic framework, dictating sentence length, rhythm, and perspective, rather than simply spitting out diffuse facts. This is George Carlin, one of the specific comedic styles used as a template for the project. The system pulls from performers with highly recognizable structural approaches to language. This emulation focuses entirely on written text structure. We are mimicking the way a comedian constructs a joke on paper, actively avoiding the ethical and technical pitfalls of voice cloning. These skill files function as rigorous analytical frameworks, forcing generic language models to output highly specific, disciplined comedic writing. The final node is MP3 radio, the orchestrator that ties the entire system together. This split screen shows the core architectural twist. The orchestrator is a declarative, plain English Markdown document that instructs Claude Code to autonomously execute Python scripts. Acting as the interpreter, Claude Code reads the assignment and begins parsing. It extracts artist and title data directly from the file names first, falling back to ID3 tags only when a track's identity is ambiguous. Voice assignment is strictly deterministic. By using fixed random number seeds, the system guarantees that the exact same comedian is assigned to introduce the exact same track on every single run. The Markdown prompt embeds a set of strict rules. It forbids fabricating historical facts, guessing at band personnel, or referencing current events. These strict guardrails ensure the generated text remains timeless. The DJ intros will make perfect sense, whether they are played tomorrow or 20 years from now. This flowchart illustrates the caching architecture. All parsed data and generated text moves into a JSON sidecar file. This creates a deliberate wall in the process, allowing you to review the text before initiating any expensive calls to the text-to-speech API. When the text is approved, the final logic maps the 7 distinct written comedic styles down to 3 distinct text-to-speech voices, grouped by their delivery energy. This declarative approach allows you to modify a complex, multi-stage data pipeline simply by editing plain English text, eliminating the need to rewrite hardcode. With the audio rendered, the system moves to the physical output generation phase, assembling the final playlist. The tracks are put through a deterministic shuffle. The playback is randomized, but the exact sequence is perfectly reproducible using a fixed seed. This diagram shows the interleaving naming convention in action. The directory dynamically resorts as numerical 3-digit prefixes are prepended to the file names, locking each generated DJ intro precisely before its target song. This specific numerical structure acts as a precompiled binary for the dumb hardware player. Because the sequence is baked directly into the file names, the device requires no external playlists, no companion apps, and no streaming connections to play the station flawlessly. We bypass the hardware's lack of intelligence entirely by shifting all sequence computing upstream into the final build process. The data flows from a messy folder of legacy RIPs through strict amplitude normalization into precise neural network trimming, and finally through an LLM orchestrator.
Kings of metal. These guys declared themselves the loudest band in the world, put it in the Guinness Book, and kept going. They wear loincloths, they swing swords, and they mean every single word. In a world of posers, Manowar is terrifyingly sincere.